In this video, we're going to talk about the acid-base reactions. Acids and bases are sort of commonly or historically recognized based on their properties, some observable properties that anyone can observe at home with certain types of substances. So, for instance, acids commonly have sour taste and will turn certain types of plant-based pH indicators like litmus to red, different color. The sour taste you might recognize from the vinegar, the acetic acid that's in vinegar, or in certain types of fruits. Citric acid, which is in lemons, for instance, so that you're probably familiar with that. Acids from in those contexts already. And then from a little bit more chemical standpoint, they react with metals, for instance, zinc, calcium, and magnesium. Acids react with these metals and produce hydrogen gas. Bases are recognized based on their bitter taste. They're kind of slippery to the touch. For instance, like a lot of soaps come from bases, and they turn litmus blue. A more sort of chemical definition of an acid is a substance which produces hydrogen ion, H plus, in water. And this is the Arrhenius definition of an acid. And we're familiar with this from earlier, in one of the earlier chapters when we were discussing nomenclature of acids. But again, we can represent, for instance, HCl gas when we dissolve this in water. So we put it in water. We can represent that, right, by writing the AQ behind the HCl. So HCl gas, the H2O above the arrow indicates that we are transferring, bubbling the gas into water. And then the AQ represents the HCl that is now dissolved in water. But the HCl does not stay intact. It's a strong acid, and so the hydrogen and the chlorine separate. The electrons in that bond go with the chlorine to produce chloride, and the hydrogen gives up the electrons to become hydrogen ion. And we represent that like this. H plus and CO minus aqueous. Both aqueous. So HCl dissolves in water. It ionizes to produce H plus and CO minus. A base produces hydroxide, which is OH minus. So you dissolve a base in water and it produces OH minus. So for instance, sodium hydroxide, so well known, solid. You put this into water, and we represent that with NaOH AQ. So NaOH now dissolved in water. But of course, this is a very soluble, a strong base and a very soluble salt, and so therefore it completely ionizes in water to sodium plus and OH minus. Okay, so see how I've separated here the sodium and the hydroxide. There's AQ behind each to indicate that they are dissolved in water. Now, going back to the acid, HCl being in water, and the hydrogen ion. That hydrogen ion is actually never free It's in the water, but it's also very closely associated with water molecules. Bound to water molecules, in fact. So water molecule shown here, an H plus. That H plus is actually attached to one or more water molecules. Here shown attached to one water molecule, and this is called hydronium ion. Since the H plus, it's very common to write the equation HCl separating H plus and Cl minus, sort of a Arrhenius type of representation of that reaction. But another way to define an acid, and it's a little bit broader definition, based on the fact that it actually HCl in water actually produces hydronium ion, is that an acid is a proton donor. So for instance, we can rewrite the above equation actually showing the interaction with water. The proton, the hydrogen on the HCl, is going to be transferred to the water as a proton, just like we showed in the above picture. And that will produce H3O plus, hydronium ion, aqueous. That leaves the chloride, and we draw that in just as it was previously. So here we have a Bronsted representation of that same reaction, right? Showing the transfer of the hydrogen ion to the H2O to produce H3O plus. Let's do another example. Nitric acid. Nitric acid, from if we represent this in a Arrhenius type of sense, then it will separate into H plus and NO3 minus, aqueous. But since that hydrogen ion is never actually on its own, it's actually closely attached to water as hydronium ion, we can represent this in a Bronsted sense, writing in the reaction with H2O to produce, through a transfer of H plus from the nitric acid, hydronium ion, H3O plus. So the acid plus H2O produces H3O plus, and then of course the NO3, the anion, is also dissolved in solution. Let's erase our previous definition. So a base now is a proton acceptor in our Bronsted definition. So an example would be ammonia. Ammonia is a weak base. Ammonia is a weak base, and when we put that into water, it will act as a proton acceptor, taking a proton from the water. Now, the proton H plus carries with it its charge to the NH3 and produces NH4 plus. This leaves behind OH minus. So in this way, the NH3, the base, is a proton acceptor, and the place where it's getting that proton from, that H plus, is from the water. When we remove H plus from H2O, that leaves OH with extra electrons, so it has a negative charge. since this is a weak base, we're going to write a double arrow. And you'll do this for any reactions involving primarily weak acids and weak bases, anytime the reaction is not going 100% to completion. So a weak base, when dissolved in water or reacting with water, for instance ammonia, only goes partially to product. And the way we represent that is then with a double arrow, the equilibrium arrow. So double arrow, indicating that's a weak base. And you'll do the same for weak acids dissolved in water, using the double arrow. Okay, so proton donor, as I mentioned before, this definition of an acid or this Bronsted definition of acids and bases broadens the definition. So now a lot of things that you may not have considered to be acids and bases will now be formally defined that way based on this definition. So for instance, water. In this reaction, water is the Bronsted base, right? Because it is accepting a proton from the HCl. The same in the reaction with nitric acid. HNO3 is donating a proton to H2O. That makes H2O the proton acceptor, and therefore a base. However, in the reaction with ammonia, right here, water is donating a proton. So in this case, it's an acid. So water can work either way. When it reacts with a base, it can be a proton donor, right, and therefore acting as an acid. And when it's reacting with an acid, it will act as a Bronsted base and accept a proton. So acid and base. This type of behavior for a compound like water has a definition or a term. It's called amphiprotic. So this means that it can both donate or accept a proton. And which thing it does is going to depend on what it is reacting with. Okay, let's erase. And let's look at some polyprotic acids. In other words, these are acids that can donate more than one proton. So for instance, H2SO4. This is a strong acid. When I put it in water, it will completely transfer all of at least one proton to the water to produce H3O+. Now, if H+ is taken from the H2SO4 and transferred to the water, that makes H3O with the plus sign. That leaves a negative sign behind and one less hydrogen to create HSO4-. Notice that the equation is always charge balance, right? So the total charge on the left-hand side is neutral. The total charge on the right-hand side, the H3O+ and the HSO4- is neutral. This HSO4- has another hydrogen which can be donated to another base. So we'll use water again. HSO4- is a weak acid, and therefore we're going to use the double arrows. But when it interacts with water, it can donate some protons to the water. Even though it's a weak acid, it'll donate some protons to produce more H3O+. Now if we remove H+ from HSO4-, that will give SO4 2- sulfate. So this is a diprotic acid. This is H2SO4 has 2 protons. The first one is strong. The second one in this case is weak, and that's something that you sort of have to memorize the list of strong acids, the list of 6 that you have in your text, and most of the other acids that you encounter will be you can consider to be weak. There'll be some exceptions. Triprotic acids. Common example is phosphoric acid, H3PO4. It has 3 ionizable protons, ionizable hydrogens can be transferred as protons, and so in a first step of this reaction with H2O, we'll show 1 hydrogen being transferred at a time. That this is a weak acid, and so we're going to use double arrows. Hydrogen is transferred to water to produce H3O plus. Right? So H plus H2O makes H3O plus. The charge goes with it. That leaves behind a negative charge and 1 less hydrogen to produce H2PO4 minus. H2PO4 minus can donate a second proton to water. This is also, of course, a weak acid. It produces H3O plus. I remove H plus from the H2PO4 minus to donate to the water. That will leave me with HPO4 with now a negative 2 charge. And the HPO4 2 minus, the hydrogen phosphate, can also give up its last proton to water. This is also weak, so we use double arrows. H3O plus, right? The hydrogen from HPO4 2 minus is transferred as H plus to H2O. H2O plus, so the proton donor, and then that leaves PO4 3 minus. Okay, so you can see all 3 hydrogens can be transferred from the phosphoric acid to water molecules. Now, these are weak acids, so these don't happen to any appreciable extent. In other words, they don't produce a lot of H3O plus, and that's represented with the double arrows. Next, neutralization. So in your textbook, neutralization is defined actually fairly strictly as being a reaction between an acid and a base that produces salt and water. And so we're going to start with this type of acid-base neutralization reaction. We'll give a couple examples. HCl plus NaOH forms water plus NaCl, and then also nitric acid plus lithium hydroxide, that forms water and lithium nitrates. Now see, both of these acid-base reactions, both are strong acids, HCl and nitric acid. These are both strong hydroxide bases. They produce water and a salt. And so this is going to be the case for these types of reactions. Anytime you have a strong acid plus a hydroxide type base, your product will be water and a salt for these types of neutralization reactions. HCl is the proton donor, and NaOH, based on according to the Bronsted definition, proton acceptor. But of course, when the H plus is transferred to the OH minus, it produces water in this case. That's the neutralization reaction. That leaves NaCl, the salt, remaining. And the same with the nitric acid, H plus and the OH minus neutralize to form water, leaving behind the salt. And so we just take the cation, the lithium cation of the base, and the anion from the acid, and they are combined to show the and written in the in their empirical formula in the product as in this case lithium nitrate. So now let's show how to represent these neutralization reactions as in different ways. I'm going to call them molecular ionic and net ionic equations, the same as we did with in the precipitation reactions between salts. In this case, we have already written the molecular form of this acid-base neutralization reaction. Okay. HCl, though, an aqueous solution, is 100% ionized. It's a strong acid, so it completely ionizes to H plus and Cl minus. Right? So completely ionizes. Right? So we can represent that, the way that we did previously, showing the separated ions, H plus and Cl minus, and we can do that also with the sodium hydroxide because it is a strong base. It will separate into Na plus and OH minus ions. So, actually in aqueous solution, this is a little bit closer to reality, right? Remember that we don't really have free ions. They are associated with water molecules like the H plus, but for simplicity, we're going to represent them this way. On the right-hand side, the products, we have water, a liquid. It doesn't ionize, at least not appreciably, and so we're going to keep that as H2O, the liquid behind it. But sodium chloride, aqueous, does ionize, right, in solution. It separates, and so that AQ can be represented as free ions, Na plus and Cl minus. The AQ indicating that, of course, that those are dissolved in water. But here we're showing them as separated ions. And this equation that we've just written is called the Ionic equation. Sometimes a complete Ionic equation. Or at least that's what is used in the precipitation reactions, and I'm using that same terminology here for the neutralization reactions. Now notice that there are some common ions on both sides, the chloride and the sodium. So since they are on both the reactant side and the product side unchanged, we can cancel them out, and that leaves H plus OH minus to form H2O. And this is the net ionic reaction for all of these types of neutralization reactions between a strong acid and a strong hydroxide base. The product will be the net ionic reaction. The net neutralization is the reaction of H plus OH minus to form water. Finally, let's look at a neutralization reaction involving a weak acid. this case, let's use HNO2, nitrous acid, as our example, and KOH, potassium hydroxide, is the base. Okay, so HNO2, the acid, is the proton donor. It will donate a proton to the KOH, specifically with the hydroxide, right? So the H plus and the hydroxide, OH minus, there, will form water. That leaves the potassium ion from the KOH and the nitrite ion, NO2 minus, from the nitric acid, and those will form KNO2, or salt. So here we have the water and the salt. Now since potassium is +1 and NO2 is -1, KNO2 is the appropriate empirical formula, and you'll have to make sure to represent that appropriately in all your acid-base reactions of this type. This is the molecular equation with everything sort of written together, and we can also represent it as the complete ionic equation. HNO2, being a weak acid, does not appreciably ionize in water. So we have AQ representing it's in aqueous water. We're going to keep the HNO2 together. It does not ionize appreciably, so in our ionic equation we're going to keep it intact as shown. KOH, however, is a strong base and a very soluble salt. It will ionize in water, K plus and OH minus. Okay, so here we're re-representing the KOH aqueous as separated ions, K plus and OH minus, as you've done before with other types of reactions of salts. And now on the right hand side, water, liquid, does not ionize, and so we're going to keep that intact, plus the salt KNO2. This is very soluble. Potassium salts are all soluble, and so we can show that as separated ions, K plus aqueous plus NO2 minus. There you go, and that is the complete ionic equation for this neutralization reaction. And notice that there's two things that we sort of left alone from the top: the weak acid, which doesn't completely ionize or ionize appreciably in water, and the H2O in the product. We still have some common ions though on the left and the right. That's the potassium. So we could cancel those to form the net ionic equation, moving down everything. HNO2 plus OH minus form H2O and NO2 minus. And that is the net ionic equation.